Hi, everyone. Okay, so I'm Andreea Buterchi. I'm the Vice President of Engineering of Veridise, and today I will introduce you to our Security as a Service platform. But before I will tell you about SaaS, let me give you a general idea about Veridise. So what does Veridise do? So there are two components to Veridise's business logic, one of which is performing Web3 security audit. But what I'm mostly excited about, and I will focus throughout my presentation today, is the Security as a Service platform. So just to give you a brief introduction to SaaS, it is a platform that allows instant access to push-button security analysis tools. So these tools are based on state-of-the-art formal methods research, and those allows developers to get audit results in real time. So now the question is, what exactly is formal methods? So formal methods is a family of mathematically rigorous techniques for automatically finding bugs and constructing proofs about software correctness. There are two categories of such formal methods techniques, the dynamic ones and the static ones. So the dynamic techniques basically execute a program on interesting inputs and monitor what happens. And the static ones basically stare at the code and analyze the program and reason about all execution paths. All right, now that we know more about the formal methods techniques, let's zoom in on the Veridise SaaS platform and see how a user can interact with it. All right, so basically a user has to first provide the source code and then a configuration file. So this configuration file indicates which tool to run and its additional parameters for that specific tool. And then under the hood, our SaaS platform runs that specific tool and then outputs an audit report. All right, so before diving deeper, I want to present some salient features of our SaaS platform. So first of all, it is powered by multiple security analysis tools with complementary strengths, and we will see that in a second. All right, it is developed in a blockchain and language agnostic way, such that it offers support for multiple blockchain languages, including Solidity, Cairo, and also Circum. All right, and it allows checking for common vulnerabilities and as well for custom specifications provided by the users. All right, so throughout this presentation, we will use a case study to showcase the features of our Security as a Service platform and also to explore how formal methods tools can be useful to prevent DeFi hacks. All right, so the case study we prepared for today is a flash loan contract. So for those of you that are not familiar with flash loans, those are a type of loan where a user borrows some assets with no upfront collateral, and they have to return the borrowed assets in the same transaction. So when this doesn't happen, then the flash loan is supposed to revert. All right. So going next, this is the logic of the flash loan contract, and it exposes a flash loan function, which is the most important function in this contract. All right, so this contract implements the ERC 3156 flash loan standard, and this function acts like this. Basically, it has three arguments: the receiver of the flash loan, the flash loan currency, and the amount to be borrowed. All right, so what we see in this highlighted block code is that if the amount to be borrowed is less or equal to the balance that is in the flash loan contract, then the flash loan is approved and the user is allowed to withdraw the specific amount. All right. Next, this contract calls this onFlashLoan method on the receiver, and it allows the receiver to do something with the borrowed money. And next, this block of code checks if the receiver returned the borrowed amount plus some fee requested by the protocol, and then it resets the balances and allowances to the initial value. If this doesn't happen, then the transaction reverts. I mean, the flash loan reverts. All right, knowing this, let's ask the SaaS platform if this contract has bugs. The first tool that we will be using is Vanguard, which is a static analysis tool that can check for common vulnerabilities, such as reentrancy attacks, flash loans, and so on. All right, and Vanguard expects the source code, as I mentioned initially, and a list of detectors to check the code against. After that, Vanguard produces a report with all the findings. All right, now we will see a demo of Vanguard. All right, so this is the interface of our tool. Basically, we start by naming a job that will run Vanguard, and we upload the source code using this interface. Now we indicate Vanguard, which is the source code, what are the dependencies, name the archive, and upload the source code. Now we will select the language, which is Solidity in our case, and configure the tool. For that, we select the detectors we are interested in, the reentrancy for this one, and create and launch the job. Right, perfect. So let's wait for Vanguard to run. And in a second, we will see that Vanguard discovers some potential reentrancy vulnerabilities. All right. Okay, so yes, we saw that Vanguard identified some potential vulnerabilities, and those are related to reentrancy, and a reentrancy occurs when a function in a contract A makes an external call to an untrusted contract B, and then the untrusted contract B calls a method in A as an attempt to steal their funds. So what is Vanguard actually telling us? Vanguard detected that the flash loan currency can be ERC777, and then this method from the ERC777 invokes an unknown callback, and after this happens, the balances field is updated based on some potentially stale value. All right, so we know that sometimes Vanguard can report potential vulnerabilities due to fundamental reasons, right? Because it's a static analyzer. So not everything reported by it is necessarily exploitable. But what we can do next is to ask another tool, which is also part of the SaaS platform, called Orca, to investigate it further. All right, so Orca is a specification-guided phasing framework that can generate concrete evidence of exploitability. So it also takes in the source code and a V specification. We will discuss this in a second. And it produces a counterexample. So this counterexample is represented by a series of transactions that violated the specification given as input. All right, so let's now see Orca in action. All right, we do the same thing. We name the job. And actually, because I have already uploaded the source code, we just select the source code, select the language. And now, as you can see, we can either provide a custom specification or choose a specification from our specification library. So in this case, the specification library exposes specification for multiple standards, so we will choose the flash loan standard. And this specification says that the balance of the flash loan contract has to be preserved. We will discuss that in a minute. All right, so we let Orca run. Okay. During its execution, it outputs some useful information for the users. It seems that it found the counterexample, and what it is highlighted here is the information with respect to the initialization of the contract, and this is the counterexample. All right, so I mentioned that Orca uses specifications. So specifications are a way of expressing mathematically the expected behavior of the source code. All right, so this specification here says that, and this specification is written in our V specification language, developed at Veridise, and it basically says that it's never the case that after a successful call to the flash loan function, the balance of the flash loan contract decreases. Basically, someone was able to stole funds from the contract. All right, so as I mentioned, Orca is able to find a counterexample for the inputted code, and the counterexample corresponds to this attacker contract. Right. So this corresponds. What you can see on the screen corresponds to the counterexample of Orca. So the first part is initializing the contract. So it basically deploys the token, the flash loan, and then it provides the flash loan contract with some amount of tokens such that it can allow flash loans, and then it performs an attack. Basically, it deploys this attacker contract, and now let's see what happens in this attacker contract. All right. So the first thing to notice, as Vanguard mentioned, is that this contract can use the ERC777 token as the flash loan currency. So one thing to notice about this specific standard is that when the transfer from is called, it actually is invoking tokens to send. So it does that only when the sender registers an interface to this token to send, which the attacker does in the highlighted code. All right, and the attack starts by initiating a flash loan by borrowing 65 tokens. All right. Now let's see what facilitated this attack to happen. So recall the flash loan contract. As you can see in there, on flash loan, when on flash loan is called, the receiver of the flash loan can do something with the borrowed money, right? Those 65 tokens. However, this call is redirected to on the flash loan method of the attacker contract, and as you can see, the attacker doesn't do anything with the money, right? And it basically returns callback success. This will bring us back to the flash loan contract, and the next block of code is executed. So basically, the new balance is basically the same because the attacker didn't do anything with the balance of the flash loan contract, and the amount to be returned by the attacker to this flash loan contract is just the fee, right? Which is 1. Orca set the value to 1. All right. Now, if you recall, the transfer from does a callback to the tokens to send function. So now let's see what happens in the tokens to send function in the attacker's contract. So in this function, the attacker attempts to transfer 42 tokens from the flash loan contract, and surprise, this transaction succeeds. Why? We will see in a second. Basically, the problem is that, I hope you can see the laser point. So basically, the allowance here is set after the transfer from call is performed, right? Which means that the attacker is allowed to transfer 65 tokens, right? And this transaction also executes because the fee is less than 42. So yeah, this was the way the attacker was able to steal funds from the flash loan because of this vulnerability. All right. Yeah, so despite looking reasonable, this contract also contained a subtle bug that was caught by our SaaS platform. And just to recap, what we discussed in this presentation is that we used 2 tools in the SaaS platform to find this serious issue. The first one was an inexpensive technique, static analysis used by Vanguard. So we employed that technique to just scan for potential issues, and then we used a more expensive technique, Orca, which is a fuzzer, that investigated further and actually generated a concrete exploit for this attack. All right, so we anticipate that this is the way or the users will interact with the SaaS platform, basically use static analyzer just to scan the code for potential issues and investigate further using another techniques. All right. So A key takeaway from this presentation is that automated formal method techniques can augment human intelligence and make it easier to catch critical bugs. And if you are interested in actually testing how our security as a service platform works, we accept beta clients for our SaaS platform. So just before wrapping up, I want to mention that Veridise is here for your security auditing needs, and we audited DeFi, AMMs, stablecoins, wallets, and also zero-knowledge proofs. And these are the clients we worked on previously. So yes, we used our tools to prove that our findings were actually correct. All right, that was all for today. Thank you very much. If you have questions, I'm happy to address them.